Okay, so next up we've got domination, which is another quite large field in graph theory. And it's a type of coloring problem, but it involves coloring the vertices of a graph with two colors, let's say black and white. And what we do is we make sure that every white vertex is adjacent to at least one black vertex. Now, in mathematical terms, what you would be looking at is, we say a dominating set of a graph G is a set S of vertices of G, such that every vertex of G is in S, and if it's not in S, then it's adjacent to a vertex in S. So essentially, S is your set of black colored vertices, and V minus S is the white colored vertices, and every white colored vertex is adjacent to at least one black colored vertex. Right, now domination. Okay, so now the question is, you want to find the smallest set S with this particular property, and that's called the domination number of a graph. That's the smallest set of that cardinality. Now, this domination problem has its origins in a chessboard problem. So suppose we want to cover the blocks on a chessboard with a queen. Now, we know what the movements of a queen on a chessboard are. A queen can move pretty much in any direction. So what we, not in any direction, but very specifically the vertically, up, down, horizontally, and it can also move diagonally. Right, so the question is, what's the smallest number of queens that I need so that I can place them on a chessboard such that every block that's not occupied by a queen can be reached by at least one queen in a single move. So what you would do is you would place your vertices on the blocks of a chessboard, and you would connect two blocks or vertices only if they can be reached in a single move by a queen placed at one point. So basically, this chessboard problem, you can model it with a graph, and it involves pretty much finding the domination number of this particular graph. Okay, so these are your two chessboard blocks. You place a vertex there, place a vertex there, and and what we do is we join these two vertices if and only if you can place a queen there, and you can actually reach that block with a queen in one single move. Right, so that's how it works. Okay, so let's example. Let's look at this Peterson graph. Okay, so what would be an example of a dominating set? We can look now. We can color that vertex red. Okay, we can color that vertex red. We can color that vertex red. Okay, is that a dominating set? Not yet. Okay, so basically that vertex is covered, that vertex is covered, that one is covered, that one is covered, that one is covered, that one is covered. The only one that's not covered is that one there, so we need to dominate that. So we can either include that vertex, or we can just include that vertex there. Okay. So if we look at the red vertices, every uncolored vertex is adjacent to a colored vertex. Okay. All right. So that is what a dominating set looks like. Now, what's the domination number of the Peterson graph? And that's a little bit more difficult to determine. So obviously the domination number of the Peterson graph is at most 4. Okay, so now you just need to go and check. You can't dominate it with one vertex. You can't dominate it with 2 vertices either. So the domination number is either between it's between 3, or it's either 3 or 4. Okay, so that's a nice little exercise to go and try and do. Okay, so another application, I mean, there are many applications of the domination parameter. For example, in a prison, the question is you want to use as few guards as possible to look, to guard the prisoners. So now the question is, again, I mean, yes, you want to minimize your costs and choose as few guards as possible. You want as few guards as possible to guard as many prisoners as possible. And so you would again model this with a graph by placing the vertex on each guard and prisoner, and you would, or each location that a prisoner or a guard can occupy, and you join 2 locations if the locations are visible from each one of the 2 points. So again, you want to color your vertices of this particular graph. You want to choose the smallest red coloring, so that any uncolored vertex is adjacent to at least one colored vertex. Okay, so I mean, there are many applications one can think of. Now, we say that a vertex V dominates W if either V is adjacent to W, or if V is in fact equal to W. So a vertex can dominate another vertex, or it can dominate itself. So a set in the vertex set of G dominates all its vertices and their neighbors. Then a dominating set S of G is a minimal if no proper subset of S is a dominating set of G. So in other words, I can't throw any vertices in my dominating set away. As soon as I throw one vertex away, or one or more, the set becomes or loses its domination property. And if the set has got the smallest possible cardinality, it's the domination equal to the domination number, the cardinality of that set. Now, as an example, both set. Now, if you go back to this example here, the red set is a dominating set, and it's a minimal dominating set because you can throw any vertex that you throw out. The set will immediately lose its domination property. Right, so let S, this is the theorem, let S be a dominating set of G. Then we say that S is a minimal dominating set if and only if for every vertex V and S at least one of the following holds. There exists a vertex W in the complement of the set such that the open neighborhood of W's intersection with S is only the vertex V. In other words, the vertex V, we say that the vertex V is the private neighbor of the vertex W within the set S. And the other one possibility that can hold, V has no neighbor. V has no neighbor in S. Okay, so let's assume, for argument's sake, that S is a minimal dominating set. Right. So let's go and let's take a vertex V there. Now this means, because it's minimal, it means that if I go and remove V, and I place V in V minus S, right, then the set is not a dominating set anymore. So what is this going to mean? It means that, okay, if V is dominated, then we are okay. Well, if V is dominated, then forget about V. What we have is there needs to be one other vertex here other than V that is not dominated. And let's say W is not dominated. So W has got neighbors. Remember, S is a dominating set. So W has got some neighbors in V minus S. And basically, it means that W must be adjacent to V, because V was in S initially to dominate W. So that is going to imply that the open neighborhood of W's intersection with S is going to be exclusive, only the vertex V. Sorry, only the vertex V. Okay, so that means V is W's private neighbor in S. Right, so the only other possibility is that V is not dominated. This implies that if V has any neighbors, they must all lie in V minus S. And that implies that there are no further neighbors of V in S. And that is going to imply that V has no neighbor. Has no neighbor. Has no neighbor in V, or rather in S minus V. Right, so basically that is proving that if S is minimal, dominating set, then we've got one of those two properties that hold. So let's say both the two properties we talked about hold, and let's prove that it is a minimal dominating set. So let's assume to the contrary that S is not a minimal dominating set. So therefore there's a vertex V that I can go and remove and place in V minus S, and my set will still be a dominating set. So if we take any W that lies there, then the open neighborhood of W's intersection, the intersection with S minus V, is not empty. Okay, it's true for all W, for every vertex other than V, right? And so the first property, if we go back here, so therefore this first property doesn't hold. Can the second property possibly hold? That is that, well, because this is still a dominating set, it means V is adjacent to at least one vertex in S minus V, and that is going to imply that V is adjacent to a vertex in S. Okay, and so that's a contradiction, because that means the second property doesn't hold, which says that the second property being that V has no neighbor in S. Okay, and we assume those two properties hold. Okay, so if those two properties hold, the assumption that S is not a minimal dominating set produces a contradiction. So therefore S must be a minimal dominating set. Alright, so the next theorem states that if G is a graph without isolated vertices, and if S is a minimal dominating set of G, then the complement is a dominating set of G. So there's S and V minus S, and we claim that V minus S is a dominating set. Okay, so let's assume that V minus S is not a dominating set. Right, so there's a vertex. If V minus S is not a dominating set, it means there's, say, a vertex that's not dominated by V minus S. So there is no edge between that vertex and any other vertex in V minus S. Okay. Right, so therefore the graph has got no isolated vertices. So it means that this vertex that's not dominated by V minus S is adjacent to at least one vertex in S, right? So that means that we can pretty much go and well, this vertex again, V, we said V is not adjacent to any vertex in V minus S. So that means we can basically take this V and we can go and place it in V minus S without without losing the domination property of S. Right, so S is not a minimal dominating set. So therefore V minus S is definitely a dominating set. What is the consequence of this theorem? The consequence of this theorem is that we can go and find an upper bound for the domination number of a graph. Right, so we know that we chose S to be a minimal dominating set, okay, and we chose V minus, and we know now that V minus S is a dominating set, right? So the domination number of this graph G is it's the minimum cardinality, it's at most the minimum between these two sets. Now, if you divide the order of a graph by 2, then the smallest between V minus S and S is going to be at most n over 2. Right, so that's a nice elementary bound for a graph without isolated vertices. Domination number is at most n over 2. Okay, so we've got that elementary bound. It turns out you can go and improve this bound. Obviously, if you make a graph denser, you add more edges or you increase the minimum degree of a graph, one would expect the domination number to decrease. And that is what we have in our next theorem, that we can actually prove that if G is a graph of order n and minimum degree at least strictly bigger than 1, then the domination number of G is at most 1 plus ln delta plus 1 divided by delta plus 1, where delta is the minimum degree again, times n. So 1 plus ln delta plus 1 is smaller than delta plus 1. And in fact, as delta tends to infinity, I mean that bound is asymptotically asymptotically small. So how would we prove this? And the way they do it is they use a little bit of probability theory. Right, so how this works is you take the graph G, and if you go and look at all the possible subsets of vertices of the graph G, right, we know how to calculate that, how many such sets there are going to be. So, I mean, you could have 1-point subsets, or 2-point subsets, 3-point subsets, and so on and so forth, right? Now, you go and list all those subsets, and each one of the subsets, you make it a dominating set. So, suppose you choose this 2-point subset. How do you make it a dominating set? By including all the vertices to it that are not dominated. Okay, So you form this list of all your possible outcomes. Each one set that's not a dominating set, we just make it a dominating set by adding the vertices not dominated to it. Right, so you get this collection of all your possible outcomes, and each one of these sets that you have is a dominating set. Right, now within this list of possible outcomes, somewhere you're going to find a set of cardinality gamma of G. Right, so that's going to be your set of smallest possible cardinality. That's a dominating set. So now you're going to use a random process. You're going to choose a vertex set with probability P, and you're going to choose it randomly. And if it's not a dominating set, you're going to make it a dominating set by looking at the vertices that are not dominated. So you want to find the expected value of this particular variable. So you want to work out the expected value. We know the smallest cardinality of a dominating set will then be at most the expected value of a dominating set. Right, so you pick, later on we'll determine what this P needs to be to give me an optimal result. So we're gonna we pick each vertex in G randomly and independently with probability P, and let X now be that set I talked about, the set of vertices, and we're going to make it a dominating set. And what we're going to do is we're going to let Y subscript X be all the vertices in the complement of the set, such that the vertices are not dominated by the set X. Now when it's not dominated, when a vertex is not dominated, it means all its neighbors lie outside of the chosen set X. Right, now taking X and putting that together with Y subscript X, that's a dominating set. We want to now work out the expected value of all of these sets. Right, so again, the expected value of X is going to be n times the probability P, and now we're going to estimate the number of vertices that are not dominated. So, the probability that a vertex is not dominated means that it's the probability that the closed neighborhood of this vertex, is not no vertex in the closed neighborhood of that vertex is in X. Right, so there's so let's, for argument's sake, assume that is my set X that I choose. Now when is a vertex Y not dominated? So let's say that vertex is not dominated. If it's closed neighborhood, which is the vertex itself plus all of its neighbors, no vertex in the closed neighborhood is in X, because if Y had a neighbor in X, it would be dominated by X, or again, if Y was there, it would be dominated by X because it would dominate itself. Right, so what is the probability that the closed neighborhood of this vertex has a empty intersection with X? Right, it's the same. Okay, so the probability that a vertex lies outside of X is 1 minus P, right? And each one of its neighbors needs to lie outside of X, which happens with a probability of 1 minus P, right? Now, what is the degree of Y? So that's going to be, its probability is going to be 1 minus P times the cardinality of its closed neighborhood, which is its degree plus 1, because we have to include Y as well. And at the very worst, that is at most this quantity here. So this quantity here reaches its maximum value when the degree of V is the smallest it can possibly be, or the degree of Y. And the degree of Y is the smallest when it reaches its minimum, which is the minimum degree. All right, so therefore the expected value of that set is at most n times that probability that we worked out, which is 1 minus p to the power of delta plus 1. So by the linearity of expectation, the expectation of this new dominating set I form by throwing all the non-dominated vertices into X is at most the expected value of X plus the expected value of Y subscript X, and it's that. Right, so simplifying, we get that expression in terms of P. And so the domination number is at most that quantity there. Now all I want to do is I want to make this upper bound as small as possible. So I want to choose the P, the probability P, that will make this upper bound the smallest it can possibly be. So we take this whole thing here, and we ask now that question, what value of P will minimize that? So we just apply calculus. So that's a little function that I have to take the derivative of. Right, now just the step in between there, what I forgot to mention is that this 1 minus P, you can actually further bound that with E minus X by noting that 1 minus X is always strictly less than e to the power of minus X. And you can prove that just by a simple derivative argument. You do that by showing that the function e minus X minus 1 minus X is always bigger than 0. One way of doing it, maybe as an exercise, go and try and do this. You take f of x equals e minus x minus this term here, and you look at the derivative of that function, and you make sure the derivative is bigger than or equal to 0, so then, or bigger than 0, so therefore it's a strictly increasing function. And what you then do is, because that's a strictly increasing function, you just look at its smallest value and make sure its smallest value is bigger than 0. And that will then mean that this f of x is always bigger than 0. Okay, so it's a little calculus argument. I'll leave that as an exercise for you guys to go and do. Right, so replacing that and bounding it, we want to find the value of P, which is going to make that term the smallest it can possibly be. And again, that's a calculus argument. You take the derivative, set it equals to 0, and you go and solve for the value P. And the value of P you get as that. And using the second derivative test, you'll see that this value P will minimize the mentioned function. All right, and then again go and plug that value of P into your original expression, and that will simplify to that result there. And again, this bound is asymptotically sharp for infinity and delta infinity. So larger you make those values, the closer this bound actually gets to the real domination number. Now, there are, in the literature, there are many variations of the domination number, and for some of those variations, they use similar statistical means to get upper bounds for these parameters.